No one understands modern AI. Each new little piece of text, known as a token, produced by ChatGPT is the result of hundreds of billions of separate calculations. The parameters used in these calculations are learned from data, by training ChatGPT to predict a single token at a time. But somehow, from just learning to predict the next little piece of text again and again across trillions of examples, what feels like real intelligence emerges. What pathways through the network's billions of computations are responsible for specific knowledge or abilities? Why do certain skills only emerge from models of a certain size, or after training for a certain duration? Are these giant models just memorizing, or are they actually learning? Today we have many compelling clues, but no definitive answers to these questions. One interesting question we can ask is how much complexity do we have to strip away before we can really truly understand a model? We know how the individual artificial neurons that make up these models work, although this did take some time to sort out back in the 1960s. As we connect more and more of these neurons together, when exactly does our understanding really start to break down? In this video, I'm going to claim that one specific example, grokking modular arithmetic with a single layer transformer, is the most complex AI model that we fully understand. This is obviously highly subjective. If you have a different example that you think fits, please share it in the comments. Your answers could make for a fun follow-up video. Like many scientific discoveries, we stumbled onto grokking completely by accident. The initial discovery led to some remarkable follow-up work that allows us to rigorously understand what the model's parameters are actually learning, why certain behaviors emerge later in training, and incredibly, we can even watch the model progress, from just memorizing training examples to learning a robust Fourier space solution to the modular arithmetic problem. This example is a few years old at this point, but it's an amazing and still very relevant way to look under the hood of modern transformers. At the end of this video, we'll also look at some more recent fascinating results from a team at Anthropic, where the team found a 6-dimensional manifold in the activations of Claude Haiku that appears to be responsible for handling the arithmetic required for the model to figure out when to create new lines as Claude writes. In 2021, a research team at OpenAI was training small models to perform modular arithmetic. If we take a mathematical operation like x plus y, we can turn this operation into a dataset by creating a table with various x values as our columns and various y values as our rows. From here we can fill in each cell with the sum of x and y. 0 plus 0 is 0, 0 plus 1 is 1, and so on. The team was studying modular arithmetic, meaning we need to pick a largest number or modulus. When our number reaches or exceeds the modulus, we divide by the modulus and take the remainder. If we choose a modulus of 5, when we reach 1 plus 4 on our table, the answer is actually 5 modulo 5 equals 0. 4 plus 2 equals 6 modulo 5, giving a final answer of 1, and so on. The modulo operation gives our model some interesting structure to learn, and nicely bounds the number of individual tokens our model needs. We know that in this case, our answer will always be 0, 1, 2, 3, or 4. From here, we set aside a portion of our data for testing and train on the remaining examples. It's worth taking a moment to consider what this dataset really looks like from our model's perspective. Our model has one input and one output for each token in its vocabulary. We need 5 tokens to represent our numbers 0 through 4, and we'll add one more token to represent our equal sign. We could also add a token for the plus sign, but since we'll only be training our model on addition, it's not needed. Having a token for the equal sign is helpful, however. As we'll see, this effectively gives our model a placeholder for its final answer. So our model has 6 total inputs, 1 for each token. For comparison, GPT-5 has 200,000 inputs, again 1 for each token in its vocabulary. To input a math problem into our model, for example 1 plus 2, we pass in the first token in our math problem, 1, into the model by switching on the 1 position and switching off all the other positions. This is known as one-hot encoding, and is how the model sees our first token. Our second token, 2, is passed into our model by switching on the second input and switching off the rest. Finally, our equal sign tells us to switch on only the final input to our model. So the math problem 1 plus 2 from the perspective of our model looks like its first input switched on, then its second input, and then its sixth input. Transformers like these are generally configured to return outputs of the same dimension that they're given. So our model's final output will also be 6 by 3. In this case, we're only going to look at the final column of the model's output. This is where we want the right answer to show up. And in this case, we want the 3 output to be switched on, since 1 plus 2 is 3. So what our model is really learning is to map this pattern of 18 values, mostly zeros, to this new pattern of 6 values. Now, imagine someone just handed you a bunch of different target input and output patterns. Here are the input and output patterns for 1 plus 3 equals 4, here's 2 plus 3 equals 0, and so on. After you saw enough of these examples, do you think you could figure out the underlying structure of the problem? This is precisely how large language models work. When we pass in the text the capital of France is into llama, for example, the token for the tells us to switch on input 791, the token for capital tells us to switch on input 6864, and so on. Moving to llama's output, the final column is maximized at an index of 12366, which corresponds to the token for Paris. It's easy to forget that the symbols we assign to our model's inputs and outputs have this extra meaning that we attach to them. But to the model, they're just patterns of inputs and outputs. Now, when the OpenAI team trained their model on modular arithmetic, their initial results were pretty underwhelming. The model was able to quickly learn to match the patterns in the training data, giving the correct output on all training examples. However, the model performed very poorly on the test set. It appeared that the model had simply memorized the training data without actually learning modular addition. But then something interesting happened. One of the researchers went on vacation, but accidentally left a model training. Returning from vacation, the researcher was shocked to discover that after a very large number of training steps, the model had suddenly generalized, performing perfectly on both training and test sets. What mechanism could possibly be causing the model to perfectly fit the training examples after just a couple hundred steps, appear to lay dormant for a couple thousand steps, and then suddenly actually learn? And could similar dynamics happen in full-size models? In Robert A. Heinlein's 1961 novel, Stranger in a Strange Land, he coins the term grokking. The book's main character, a human who is raised on Mars and returns to Earth, uses the Martian word grok throughout the book. Grok has no direct translation from the far more complex Martian language, but one meaning is to understand something so thoroughly that you merge with it and it merges with you. The OpenAI team was able to replicate the sudden generalization phenomenon across a range of arithmetic operations and model configurations, and in January 2022 published this paper, where they called the phenomenon grokking. Grokking is a provocative name, but the phenomenon itself is shocking. What could be causing the model to suddenly perform perfectly on the test set? A year after the publication of the OpenAI grokking paper, a team led by researcher Neel Nanda published an incredibly detailed analysis of the phenomenon. Their paper digs deep into the model's parameters and activations to produce a very satisfying and elegant explanation. Nanda and his collaborators studied a single-layer transformer. This is the same architecture used in most large language models, just with fewer layers. A transformer layer is composed of an attention and multi-layer perceptron compute block. As we saw with our toy example earlier, our data is fed into our model using one-hot vectors. Nanda used a modulus of 113, so the model's input vectors are of length 114, with 113 positions for the digits 0 through 112, and a final position for the equals sign. So to ask our model what 1 plus 2 is, we pass in this 114 by 3 matrix, made up of all zeros, except for a 1 in the 1 spot of our first column, a 1 in the 2 spot of our second column, and a 1 in the equal spot of our final column. From here, our 113 by 3 matrix is multiplied by a matrix of learned weights known as an embedding matrix, producing 3 new vectors of length 128 each. These resulting embedding vectors are no longer sparse, and as we'll see, contain some interesting structure. From here, our embedding vectors are passed into our attention block, and then our multilayer perceptron compute block. The output of our multilayer perceptron is of length 128. We multiply this output by an unembedding matrix to compute a final vector of length 114. The model's answer is given by the largest value in this final vector. So if our model is working well, its maximum output value should occur in the 3 position, corresponding to the correct answer, 1 plus 2 equals 3. Training this model on modular addition, we see the same grokking behavior observed by the OpenAI team, with the model first memorizing the training data after around 140 steps, and then generalizing after 7,000 training steps. Let's explore the model's intermediate outputs, better known as activations. Specifically, let's have a close look at the outputs of some of the neurons in the second layer of our multi-layer perceptron block. This layer has 512 total neurons. If we pass in the problem 0 plus 0 into our network, the first neuron of this layer returns an output value of 1.17. Our second neuron returns an output of 0.6, and so on. Now, let's visualize how these values change as we change the input math problem. Let's fix the value of x to 0, and explore a range of y values, starting with 0 plus 0, then 0 plus 1, then 0 plus 2, and so on. Sweeping through all 113 possible values for y, we see some interesting structure, with the outputs of some of our neurons looking like sine waves. Digging deeper, let's explore the correlation between all the different pairs of these neurons. Let's color our points using the input y value to our model. So our neuron outputs given the input 0, 0 are colored purple, and outputs given the input 0 plus 112 are colored yellow. From here, we'll create a 7 by 7 grid of scatter plots for each pair of neurons. So on our second scatter plot on our first row, for example, we'll plot the output of our first neuron as the y value, and the output of our second neuron as the x value. Bringing our 2 waves together like this results in a nice loop shape. Creating the same plots for each pair of neuron outputs, we see more interesting structures. So our model has clearly learned some type of structure, but could this structure be related to grokking? If we move backwards in our training process and visualize these structures as we go, we see that by the time we reach our model that just memorizes our training set, these structures completely disappear. So while this early model performs perfectly on the training set, we don't see any evidence of the waves and loops that we see after grokking. So perhaps these structures are related to why the model groks. This video is sponsored by me. The Welch Labs team and I have written a whole new book on AI. It's beautifully illustrated and is a great way to dig deeper into the topics we cover in these videos. Each chapter includes thought-provoking exercises and supporting code. Our first print run is totally sold out, but we have another batch coming quickly in January. And if you order now, I'll send you a discount code for a free download of the ebook version. Books and education are really near and dear to my heart, and we've poured a ton of effort into this book. I really think you're gonna like it. Now, back to grokking modular arithmetic. The wave shapes and loops we see inside our model as it groks suggest that the model is potentially computing and making use of the sines and cosines of our inputs x and y. If we take a discrete Fourier transform of our activation pattern, we can compute the frequencies of the waves learned by our model. This first wave yields a largest frequency component of 8 pi over 113, and our third wave shows a largest frequency component of 6 pi over 113. If we plot these waves on top of our model's outputs, we see nice alignment. Let's look for these frequencies in other places in our model. Let's visualize a single value in our first embedding vector. Just as we did with the neurons in our multilayer perceptron, let's plot this value as we sweep through a range of input values. Note that our first embedding vector only depends on our first input x. So here we'll sweep from x equals 0 to x equals 112, while keeping y fixed at 0. We don't see quite the same smooth plots that we saw earlier, but if we compare our curve to a cosine wave with a frequency of 8 pi over 113, we do see reasonably good alignment. Part of the challenge here is that this early signal in our network also appears to contain higher frequency information, which makes sense given that we found evidence of multiple frequencies later in our model. We could analyze the frequency content of our full embedding vectors at this stage of the model. But for now, let's build what's known as a sparse linear probe. If we sample the values at a few more positions of our embedding vector, we see similar semi-periodic curves. Now, it turns out that if we take a weighted sum of these 8 curves, we end up with a curve that looks very close to a cosine curve, with a frequency of 8 pi over 113. The weighted sum is very relevant here, because taking weighted sums like this is a big part of what our attention and multilayer perceptron blocks do, meaning that these compute blocks have access to a very clean cosine wave. The signal is just spread across a few different locations in our model at this stage. We can compute a similar sparse linear probe for the sine of x times 8 pi over 113. Now, our first embedding vector only depends on our first input x, and our second embedding vector only depends on our second input y. These inputs are combined in our attention block. Since the same embedding matrix is used to process our 3 inputs independently, we can use the same sparse linear probe on our second embedding vector, and we'll see the same nice cosine and sine curves, but now as a function of y. So very early in the model, our model learns to compute the sines and cosines of our inputs. But why? What did these functions from trigonometry have to do with learning modular addition? The modular addition problem may seem a bit foreign or contrived, but we actually do it all the time. A 2-hour meeting that starts at 11 a.m. will end at 11 plus 2 modulo 12 equals 1 p.m. Analog clocks are implementing modular addition physically. Each hour that ticks by adds 1 with the hour hand, and the circular motion of the hands perfectly matches the modulo arithmetic problem, starting over when reaching 12. Now, as we saw when probing the neurons in our multilayer perceptron, our network learns to form circular patterns in its activations. Could these circular structures be solving the modular arithmetic problem in the same way that an analog clock does? The sines and cosines we see computed by our model in its first layer could be part of this puzzle. If we put the output of our sparse cosine probe on an x-axis, and the output of our sparse sine probe on the y-axis of a scatter plot, we get a nice circle when we sweep through our input values. However, it's not enough to learn a circular structure for x and y independently. Our network has to figure out how to actually add x and y together. Adding x and y may seem trivial for our model to learn. After all, neural networks are literally built from a bunch of adds and multiplies. But remember that we aren't actually passing in, for example, the number 2, or a direct representation of it. Instead, we're switching on the input to our model that we have labeled 2. The network cannot just use one of the additions in one of its neurons to add x and y together. What happens instead turns out to be way more interesting. It is straightforward for our attention layer to add together the various sines and cosines computed by our first layer. Our attention layer could easily compute cosine x plus cosine of y. However, that's still not what we need to solve the problem. We need to add together x and y themselves. In our clock analogy, we need to add the angles of the clock hands, not the sines and cosines of these angles. Let's return to the second layer of neurons in our multilayer perceptron compute block. Earlier, we explored how these neuron outputs changed as we varied a single input. Let's now explore how these outputs change as we vary both x and y, to see if we can figure out how our network is bringing these variables together. Again, visualizing the output of a single neuron. If we keep y fixed at 0 and sweep through all possible x values, we get a familiar wave shape. Now, let's add another axis to our visualization, and plot our neuron's output now as we vary y. Let's explore all combinations of values for x and y. With this many points, it's easier to visualize our neuron's outputs as the height of a surface, where the color of the surface corresponds to our neuron's output value. Like many of the outputs we've seen so far, our surface is approximately wave-like. What combinations of sines and cosines best capture this wave structure that our network has learned? As we did earlier, we can take a Fourier transform, but this time with respect to both x and y. Extracting our top frequencies, we can decompose our surface into a few key components. This component is the cosine of x, and this component is the cosine of y. This top component is the strongest and the most interesting. It's equal to the cosine of x times the cosine of y. So the strongest frequency component of our surface is equal to the product of the cosine of x and cosine of y functions that we saw computed earlier in our network. Now, it turns out that it's more natural for our network to take a sum of sines and cosines than a product. I'll put a note about this in the description. So why are we finding a strong product like this in the middle of our network? And does this get us any closer to actually computing the sum of x and y? Remarkably, it does. Let me show you one more thing. Let's go one layer of neurons deeper into our multi-layer perceptron and plot the outputs of a neuron in this layer as a function of x and y. We see similar wave-like shapes here, but the wave is less regular, and it moves diagonally across our surface. This orientation of the wave is really important. Consider these top two crests, where the output of our neuron is maximized. Let's move to an overhead view and look at the combinations of our input values that fall on these wave crests. The first crest starts at x equals 0 and y equals 65. Moving along our crest, we find intermediate values at x equals 20 and y equals 45, x equals 40 and y equals 25, x equals 60 and y equals 5, and finally x equals 65 and y equals 0. All of these pairs of inputs add to the same value of 65. So this neuron fires maximally when x plus y equals 65. In its own specialized way, this neuron has learned to add. Or more precisely, this neuron fires for any pair of inputs that add to 65. Our second wave crest starts at x equals 66, y equals 112. From there, it moves through values like x equals 91 and y equals 87, and ends on x equals 112 and y equals 66. Adding these pairs together, we get 178 in each case. Recall that our model is trained on modular addition, with a modulus of 113. Our result of 178 modulo 113 is 65. So this second crest also finds pairs of inputs that add to 65. But how in just one layer of neurons do we go from products like the cosine of x times the cosine of y to actually adding together x and y themselves? Here's the output of another neuron in the second layer of our multi-layer perceptron. The strongest frequency component here is sine of x times sine of y. Now, each neuron in our following layer takes a weighted sum of the outputs of the neurons in our current layer. Let's consider how this weighted sum causes our surfaces to interact. We saw earlier that our first neuron's output has a strongest frequency component of cosine of x times the cosine of y. And our new second layer neuron has a strongest frequency component of the sine of x times the sine of y. Let's assume for a moment that the weight assigned to our cosine x times cosine y neuron is 1, and the weight assigned to our sine x times sine y neuron is -1. Visually, this negative weight flips our second surface vertically. Now, when we add these weighted surfaces together, the sines and cosines remarkably interfere in just the right way to create the diagonal symmetry that we see in our neuron in the following layer that allowed our neuron to fire on combinations of inputs that add to 65. As you may remember from trigonometry class, the cosine of x times the cosine of y minus the sine of x times the sine of y is actually a trigonometric identity. specifically a sum of angles identity that exactly equals the cosine of x plus y. This identity allows us to convert the sum of products of sines and cosines into a sum of x and y, which is exactly what our network needs to compute. And remarkably, the network appears to have learned to effectively use this trigonometric identity to solve the modular addition problem. And remember that our training data is just these sparse patterns that have nothing to do with sines, cosines, or trigonometric identities. The final unembedding portion of our model takes one more weighted sum, this time of the outputs of the final layer neurons in our multi-layer perceptron. Visualizing the outputs of a few more of these neurons, we see the same types of diagonal symmetries, with various shifts and scales. Our unembedding layer takes different combinations of these outputs for each possible token that the network could return. Here's the resulting surface for the 7 output. As we saw with our multi-layer perceptron neuron that detected all combinations of numbers that added to 65, this surface reaches a maximum for all the combinations of x and y that add to 7. Here's 7 plus 0, here's 0 plus 7, and here's 3 plus 4. So remarkably, to solve this modular arithmetic problem, our network learns to numerically estimate the sines and cosines of our inputs, computes the products of these functions, and then uses a clever trig identity to create the diagonal symmetry needed to solve the modular addition problem, and then brings multiple versions of these resulting patterns together to compute a final answer. Now, can this detailed understanding of how the model solves modular addition help us understand why it groks? Let's watch the training process again, but this time while visualizing the evolution of the various structures learned by our model. After a few hundred steps, our model perfectly fits the training data, but we don't yet see any hints of sines or cosines. As our model continues to learn, its performance stays flat, giving the appearance that nothing is happening. However, as we can now clearly see, under the hood the model is starting to piece together the relevant structures needed to solve the modular arithmetic problem. This is such a wild phenomenon. It's very common to visualize training and test performance as a model learns. And when both metrics are flat for this long, the typical assumption is that the model is done learning and has settled into a stable solution. Neel Nanda and his co-authors propose a clever new metric in their paper called excluded loss. Note that thus far we've been plotting the model's accuracy as it learns. And here we'll switch to plotting the model's cross-entropy loss, so lower values are better. See my gradient descent video or chapter 2 of my new AI book for more on cross-entropy loss. Now that we know that our model is operating in the frequency domain at a few key frequencies, what happens when we remove the information at these frequencies from the model's final output before measuring performance? Removing the 8 pi over 113 frequency that we found, and plotting this excluded loss as the model learns, we see our new metric dip down quickly with training loss, but then slowly climb as our model builds the sine and cosine representations. This excluded loss increases because we've taken away the model's ability to use this key frequency. And importantly, during this long period of flat training and testing performance, our excluded loss slowly climbs, showing that our model is making more and more use of patterns at this frequency. Interestingly, Nanda and his collaborators show that grokking occurs not necessarily when the sine and cosine structures are completed, but just after, during a phase they call the cleanup phase, where the model actually removes the memorized examples that it relied on early in training. These dynamics are fascinating and explain very nicely why this model groks on this problem. It's so satisfying to me that we can take apart this model, understand the actual mechanisms that it learns, and then use these mechanisms to design a new metric that clearly shows the model's slow progression from memorization to learning, and that nicely explains the surprising grokking behavior. This level of clarity is a beautiful and rare exception in modern AI, a transparent box in a world of black boxes. The approach Nanda and his collaborators used to perform this analysis is generally known as mechanistic interpretability. Since Nanda's paper came out in early 2023, we've seen some really interesting progress in this field, but are still very far away from anywhere near this level of understanding of full large language models. There's some recent work from a research team at Anthropic that gives a nice feel for the current edge of our understanding using this type of bottom-up mechanistic interpretability approach. The team studies how a full-sized model, Claude 3.5 Haiku, figures out when to create line breaks when writing. The team finds that the Haiku model represents the number of characters that it's written on a given line on a manifold in 6-dimensional space. This structure is somewhat analogous to the loops that we saw in the multi-layer perceptron of our model. To figure out when to insert a line break, Haiku needs to know both how many characters it's written on the current line and how many characters long the lines of the text it's currently writing need to be. Using linear probes, similar to the ones we used here to find the sines and cosines early in our model, the Anthropic team mapped character count and line length to this 6-dimensional manifold, and found that Haiku represents these concepts in this space in a very similar way. This 70 character count probe lines up right next to this line length of 70 probe, and so on. Now, this gets really wild when these representations are passed into Haiku's attention blocks. We see what the team calls a QK twist, where these helix-like geometries are rotated relative to each other in this 6-dimensional space. After rotation, the probe for a character count of 70 is now closest to a line width of 75. And we see a similar offset of 4 to 5 characters across the length of our curve. The proximity of these points in the model's attention heads leads to a high dot product when the model is about 5 characters away from the end of a line. The team goes on to show that there are multiple attention heads that specialize in detecting various distances from the end of the current line of text. And this mechanism allows Haiku to precisely estimate how much more room it has before the end of the line. Now, compared to Claude Haiku's full range of capabilities, deciding when to create a new line is very simple. However, it is exciting to see that the Anthropic team found such a clean mechanism that controls this behavior in a full-size model. The story of grokking is such a nice arc of scientific discovery and progress. We accidentally discovered a new phenomenon, and the search for an explanation genuinely helped push forward our understanding of model training dynamics and the inner workings of transformers. The names we give our discoveries matter, and I like the name grokking. It feels alien, and originates from the complex Martian language in Heinlein's novel. The AI researcher Andrei Karpathy recently commented that training large language models is less like building animal intelligence, and more like summoning ghosts. You can think of a ghost as a fundamentally different kind of point in the space of possible intelligences. The literal meaning of grok, to understand something profoundly and deeply, is a nice fit for what the model appears to be doing. But what I really appreciate here is the connotation of this thing being alien. I think it's a really nice counterpoint to overly personifying models. We communicate with these models in human language, but as we've seen, this is a thin veneer. If we go one layer deeper into what these models actually process in return, we find these absurdly complex patterns. As we build more intelligent models and learn more about how they work, it will be fascinating to see if these artificial intelligences feel more alien, ghost, or human. I am tired, so this has been my first full year working fully on Welch Labs. We made some progress, so we did 9 videos this year, and we did 1 book. And man, getting that done filled like every available second of time that I had. For now, on the business, I'm trying to keep things simple. So really just focusing on making sure that the business and the channel work well enough to support my family and I. I left my full-time job last year. My goal is to earn as much from Welch Labs as I did from my engineering job. I was hoping to replace my whole income this year. It's probably gonna be like 75%. The book helped a lot, but there's always challenges. The business side is hard. I've tried to do this full-time before, once in 2018. I just didn't have enough runway and enough focus on the business. So I think we're doing it right this time, but gosh, it takes time, and man, it takes a lot of work. So I hope you enjoyed what we've done this year. A lot more of it next year, kind of working on the focus and direction for next year right now. But I'm really happy with the book. I hope you're able to get a copy. I know we're not shipping internationally yet. That will be a focus early next year, I promise. But yeah, what a year. Man, thank you so much for your support. If you are able to support on Patreon, that helps a ton, or just liking and sharing the videos. Thanks for a great year. I'll see you next year.